Your slides are not visible here.
Is it now, sir?
It has not come, Suryanarayan. Slides are.
Dr. Jisha. Mr. Suryanarayan, your slides are not visible.
Oh, one second. Is it coming now, sir?
Yeah, coming.
Oh, all right. I'm sorry, there has been a mistake.
Okay, now it is okay.
Right. So, is it visible now? Can I go back and come again?
It will be good. It will be good if possible.
Right. So, anyway, this was the beginning slide.
Yeah.
And I would like to resurface my discussion here. We begin with our CFRP measuring properties, and this CFRP has the fractural behavior where it exhibits complicated fracture structure depending upon its anastrophe of the member and the direction of the stress principal axis. As you can see, there are quasi-isotropic CTT and CMT type of structures which can determine the CFRP materials. And these are various and very highly functional materials such as thermoplastic CFRP, where it has different combinations of fibers and matrix.
Suryanarayan, sir?
Yes, sir. Yes, ma'am.
Interrupting once more. Your slides, can you put in the presentation mode? Now we can.
Is it available?
Now, yeah, you now click on the presentation mode. Yeah. Okay.
Is it okay now? Okay.
Yeah. Okay, sir. Okay, thank you.
Thank you. Right. So since undergoing to the continuing to our discussion, so this CFRP test can perform on tensile, compression, bending, and inclined shear test. As we can see, these are the stress and strain graph, which will provide us the analysis of our CFRP samples. We can evaluate the CFRP samples right from on its material testing mode, and we also perform it on CAE model, where we have the analysis softwares which will provide us the stress distribution, and we can also predict the performance of the CFRP materials with simulating the samples. These are the test jigs as per our ASTM standards. As we can see here, there are almost 4 different types of standards which are mentioned. And each standard has different types of samples to be prepared according to the reference data provided by our American Standards of Testing Society mentioned. As we see here, we notice an open hole compressive strength jig. There is also the ASTM standard, which is mentioned as ASTM D6484 and D6484M. So this 6484M stands for mandatory clause of framing the specifications for the sample preparation. So in ASTM D6484, we need not have to prepare the exact sample dimensions. It can be variable, but as per D6484M, it has to be very mandatorily followed as provided in the ASTM regulations. And there are several types of standards to begin with in the ASTM accreditation, which has different types of materials, starting which it covers from iron, steel, non-ferrous metals. It also covers up all customized materials as well. Moving on to the next slide, we shall be seeing the in-plane shear test jigs here, and I can point out the different types of structures which we see in the grips dimensions. the ASTM D5379, which is called as IOSEPS-Q. And we also have ASTM D7078, which is our another in-plane shear test. So these are basically to provide the analysis of in-plane shear properties of composite materials, which are tested by and estimated by various testing methods. In this case, we selected these 3 shear methods just because of several sample dimensions which has discontinuous carbon fibers. Now we can see in the in-plane shear test, as per ASTM 5379 IOSEPS-Q, we start to evaluate the area from narrow to a large section. So the smaller the sample of carbon fiber reinforced plastics which we produce, it can be accommodated with our different types of grips. In this case of unevenness in the material, the small samples which has narrow evaluations area are very sensitive about the local strain. So it is very mandatory that we need to choose a very optimal jig for such a kind of a material. These are the types of sample which can be prepared. And as we can see, different holes in these sample, and there is a V groove of bigger area in this sample, and it slowly narrowed down here on a very smaller note. So based on these kinds of areas, we can see this unevenness can be properly adjusted on choosing the right jig. So this is another example where we saw previously. As per our ASTM 5379, the jig is mounted in between. We mount strain gauge sensors in the middle, and this has been properly set to make sure this will be a compression test, and we choose this area to analyze. When the tests are performed, we can see deformation here, and this has been distributed. These are highly sensitive tests, and you could also see a larger specimen of carbon fiber reinforced plastic, which is measured here, and this can be analyzed through our DIC camera, which is to have a digital correlation imaging. The test which we have see here is showing the indication of how the sample stress and strain are calculated. As we see here, the stress is slowly increased, and thus it can be measured from the front and back side of the sample. It is also equated with the stress along with the distance. So each of these grips are providing us with different kinds of data, right from our stress and strain. This is an observation example of strain in an in-plane shear jig, as we see here on 2 different types of samples. This is the sample initially mounted on the jig, and this has been observed through a DIC camera software as well as a suitable camera where it identifies the structural deformation during the test. So as we can see slowly here, the color is getting deformed on stages, and this is where the stress is being distributed from towards the other parts of the sample. This is essentially to understand the strain and stress happening during the actual samples where we produce for our activities and our requirements. We could also see in this area, in this sample, since this is a larger sample, we have a great field of view. And as we see here, this is where the stress is analyzed gradually from this point and slowly dispersing to the other parts of the area. And here the specimen has been on high stress. Shimadzu has a very unique software and accessories for these kinds of testing to perform on a CFRP samples. Coming to the following for as per our ASTM standard on other parameters. Apart from our in-plane shear jig, we also have different types of compression test jigs. It is called as the CLC compression test, which can also be called as combined loading through compression test. And this is the overhead combined compression test. And this is the combined actuated compression. See here, this test jig is to have a test method on in-plane strength, loading a shear force and compressive force on end face and measuring the in-plane strength of the elastic modulus. Each of these jigs has different and unique properties to analyze the samples. The OHC compression test can provide test method for open hole compressive strength for evaluating the rivet hole which is getting to be corrected. This CAA compression test is for measuring the test method of compressive strength after an impact. We now slowly move on to plastic tensile as per our ASTM and ISO standards. Essentially, when we see in our global accreditation extensometer, or I should say the strain gauge extensometer selection and its accuracy, we will be determining the elastic modulus inside with these kinds of applications and standards. We will be having a set of specimens which is studied in ISO 527. As we can see, the preferred specimen will always be 1A, but in ISO 527, there are different sets of sample dimensions. As we can see here, each and every sample will be prepared according to the specified ranges, and slowly and steadily we have different sets of gauge lengths and dimensions deforming to the smaller size to the larger size. When we are into our educational research, and ideally we will be working on dimensions 1A and very uncommonly at 1B. This is essentially to suit our industry's products to fit into the samples dimensions. And now we see about ASTM D638. And when we see here, these are of 5 types. So if we see out here as well, the preferred specimen will always be type 1. And we use type 2 in case of breakpoint is out of the parallel area. And we only use type P if the testing has to be done on a thermostatic chamber. A thermostatic chamber will always provide you a temperature control test where it can go up to even 800 or 1000 degrees Celsius on a furnace. Here if we see, the samples length are differed each and every type, and we also see the parallel area initial type 3 samples, and we also see the gauge length as common for most of these types with 50 mm. This 50 mm gauge length is essentially most commonly used for plastics in tensile test, and it gradually varies from 25 mm to 50 mm and even up to 75 mm. Now, these are the revisions which has been recent on standards. This is to determine the tensile properties from International Organization of Standardization through our standards through global parameters. And here we see A revision version was issued during our February 2012, and now we have gauge length which is selectable from 20, 25, 50, and 75 specifies of sampling requirements for data acquisition, and the changes of the yield strain calculation, which is on the method of nominal strain. Increases the probability within the gauge length, which might decrease your extensometer, will be your better option for performing the ISO 527 test. Here we see the ISO 527 in detail. As we can see here, the extensometer specifications which are required varies from 20 to 75 mm, and it must also should comply with ISO 9513 standard calibration for the extensometer. And since we see here, when the gauge length is set for 75 mm and 50 mm, these are the this would essentially bring us a better resolution in 50 mm gauge length than in 75 mm gauge length. But previously, gauge length 75 mm was not available. On a recent revision, this has been included by the ISO standards. We also have a small tabular column here, which provides us the class of extensometer. The class of extensometer is what we determine as the extensometer's accuracy. The accuracy varies from 0.2% to 0.5 and maximum 2%. It reciprocatively provides the following relative error and its resolution based on the class of extensometer. Moving on to the next information, data sampling. Any test which we perform, tensile, it could be compression or bending. Data sampling is one of the vital information which we get out of our system. So the universal testing machine which we use must comply with ISO 7500 class 1 rating, where the data sampling will provide us enough of information on plotting the stress and strain graph. This sampling rate is for data acquisition must be at least as high as the sampling frequency calculated based on the following conditions. We terminology the F as our sampling frequency, V as the test speed, L as in the gauge length, and L as in the grip space, and R as the minimum extensometer resolution required. Amount of sampling frequency rate, which provides the frequency as well as the test speed, and narrow down to our extensometer resolution at the last. This must be able to acquire 3 types of data: the test force, the grip space, and the extensometer data. If only 2 types of data can be required, then it should be possible to acquire the entire test force and extensometer data. The sampling rate data was not available initially on the ISO standards and revision. And once we get the sampling data, next step comes the data processing. So the software has to have a processing of data where we see the nominal strain is calculated in the following method. The following method B was added for measuring the strain after the yield stress is applied. When we see the yield strain and the increase in the grip space of the yield strain provides a relationship with the initial grip space. This was previously on the post-yield strain, which was calculated with the formula using our method A. Now it has been revised to method B. When we look into our Young's modulus calculation, we can see 2 types of method as secant method and regression method. Now you also understand from this graph, using an extensometer, the type of data which we get and where the data will essentially plastic region, as you can see. This is the most important working area on any sample from the extensometer to understand the material's properties. So this part of data is very vital and it can give a very accurate data from our extensometers. And this is the data where we get it from the grip space, which is basically the. Now, for these kinds of analysis, what is the basic or standard requirement of testing machines which you require? You need to first understand the force measurement of the machine has to be plus or minus 1%, and the ASTM standards as per E4 class, it has to be ISO 7501 as per. So all these will satisfy with our Shimazu's AGX-V series, where we have different ranges, and AGSX series, which has our standard ranges. Here we can see the sampling rate is 1 kilohertz for AGSX, and this complies with the ISO standards. We shall be getting into our specifications in the last PT slides. Now, coming to extensometer. The extensometer which we see here is a automatic extensometer, and 50 mm and 70 mm, 75 mm. And these are by adjusting the supporting lens on the sample. As we can see here, for accuracy in the measurement range of 0 to less than 0.2 mm, this extensometer has the accuracy of plus or minus 1 micron. Measurement range from 0.2 mm or more, the accuracy is plus or minus 0.5% of the indicated value, which again, as per our ASTM and ISO standards, this extensometer is very good, very essential for our testing of elastic modulus on our plastic samples. We can see the gauge length setting rods, which is available here to adjust from 50 mm or 75 mm. There are also different types of extensometers available. This is the manual extensometer. As we can see here, this has a standard fixed 50 mm gauge length. And here the accuracy again varies from 0.2 mm to less with 1 micron, range from 0.2 mm to 5 mm at 0.5% of the indicated value. This resolution will also vary from, this is an one-step attachment process where we just clip the extensometer onto the sample and run the test. And finally, we have a manual extensometer. This is a standard extensometer which we can see even in our day-to-day labs and other tests. This has a gauge length of around 75 mm, and as we can see, in this type of extensometer, this is always an adjustable extensometer. Measurement range is plus or minus 1.5 micrometer from the measurement range of 0 to 0.15 mm. And the resolution also varies from 0.15 micrometer to 0.75 micrometer. This is the most advanced extensometer in our industry. This is a non-contact type extensometer. This extensometer essentially will have no contact with the sample, and we have a video camera to analyze the test. As we can see here, the cameras are mounted on the machine, and this also satisfies the ASTM D638 and ISO 527 standards. The tests are performed by using a very easy to operate software where the machine need not have to be calibrated separately or attachments of the tedious. The camera are already mounted in the machine, so we can have a plug and play kind of a test from the machine. What are the major advantages? The test samples are tested without contacting them, and there is no negative effects from contacting samples, and it can even measure the width of the sample. It can test a diverse range of samples such as plastics, films, and rubbers. So when it is a contact type extensometer, we need to understand whether the extensometer is firmly fixed with the sample. We need to change the fixing modulus to have a better gripping. It is also very easy to measure the elongation in a thermostatic chamber, wherein for standard type of extensometers, it requires a very special one to put it inside the extensometer for high temperature resistance. And another advantage is it can also measure the width, which is to measure the Poisson's ratio measurement. When an extensometer is connected for tensile test, the essential purpose of an extensometer is to understand the difference in length. But wherein when we use our non-contact extensometer, it analyzes both the length as well as the width of the sample, where you get both the results out of one test. So this is the mission. This is the non-contact extensometer which is available in our Shimato. We shall slowly move on to Flexural properties of plastics through ISO 178 and ASTM D790. Now we will be having an analysis of what is the difference between the ISO and ASTM on Flexural testing. So here we can see the differences of ASTM and ISO standards. It varies in thickness, it varies in width, and it also changes in the accuracy on its own. We can see here the test speed is 0.1% minimum. Here it is 2 mm per minute. And here the deflection measurement system, it is necessary with a very specific target. And here we can also see the determination of elastic modulus, which is available from these ASTM and ISO standards. Now, when we come to jigs and its test speed, we need to have a 3-point bending jig. And when we see on ASTM D709 method, or D790 method, I'm sorry, it has been misspelled. So the punch radius has to be R5, and the support should also standards, these are variable. The punch can be of R5 mm, wherein the thickness can be 3 mm, which is R2. When the thickness is over 3 mm, it can be R5. So these are very variable and flexible. But the length of the span remains the same, along with the deflection measurement system. And for the test speed, if we see, when we follow procedure A for it is 1% per mm, and procedure B, it is 10% per mm. Whereas in ISO standards, it is 1% from 5% to 50% on after modulus. So these are very fixed, and these are followed in the ASTM and ISO standards. Moving on to the next slide. When we see about the 790 procedure, what is procedure A and what is procedure B? When we see in the procedure A, it is easy to apply on the hard specimens, where especially the case of measuring the Young's modulus is essential. Whereas in procedure B, it applies to soft specimens, and it is especially in the case of measuring the flexural strength. So these are the two types of procedures which are available in D790, and this varies from the sample materials which we test. How do we determine the elastic modulus? Here we see on ASTM D790 and ISO 178, tangent, secant, and chord is what we measure in D790, wherein for ISO 178, we have a thick blue line which has the measured area. For ASTM, we have 3 different parameters to analyze these things. You can see the percentage of A and B, which is calculated as per a stress and strain curve, and most of the working area will be before A%. And what are the revisions which is now followed in ISO 178 for flexural standards? There are 2 types of testing conditions are now selectable, and we need to have a deflection measurement device which is necessary as per our recent revision. When we come to the testing control, the test methods initially the method A was available, where the test can be performed using either of the following two test conditions: A, at constant speed through overall testing, and B, at 1% per minute during elastic modulus and 5% per minute or 50% per minute after the elastic modulus measurement. Here we can see the method 1 and the method 2. So now we have a difference in the method B, where only 1% is carried, whereas in method A, we constantly follow only one test speed. So the method B is a very recent revision, which gives us more accurate data. Now we can see this is the method A, where the sample is tested and it is done in a very uniform method with speed, and it comes back. And finally, it goes down for the overall testing. In method B, we have 1% per minute in the elastic modulus measurement, and again continuing to 5% or 50% in the elastic modulus measurement later. For this, we require